Welcome to học tiếng Anh với Joseph, where we build vocabulary and practice pronunciation through reading. Continuing with The Cat in the Box, A History of Science in 100 Experiments, today we will read story number 74, Artificial Radioactivity. Hôm nay chúng ta sẽ đọc câu chuyện số 74, Artificial Radioactivity. Marie Curie had investigated and named radioactivity at the end of the 19th century. In the 1930s, her daughter Irene discovered a way to manufacture radioactive elements artificially. Irene worked with her husband Frederick. He had originally been known as Frederick Joliot, but when they married, Irene and Frederick each took the surname Joliot-Curie. The Joliot-Curies worked at the Radium Institute in Paris, which had been founded by Irene's mother and is now known as the Curie Institute. There, they had access to the world's largest supply of the highly radioactive element polonium, discovered and named by Irene's parents. Polonium is a strong emitter of alpha particles, and in the 1930s, the Joliot-Curies were investigating the effect of this radiation on other elements. In January 1932, their experiments showed that when beryllium was bombarded with alpha particles, it emitted another kind of radiation, which was very difficult to detect, but which could knock protons, which are easy to detect, out of the nuclei of the atoms in paraffin. James Chadwick, working at the Cavendish laboratory, followed this up, and within a few weeks had identified the previously unknown radiation as a stream of electrically neutral particles, each with about the same mass as a proton, which became known as neutrons. In 1935, he received the Nobel Prize in Physics for the discovery. Meanwhile, Irene and Frederick had continued their experiments. At the beginning of 1934, while studying the effect of alpha radiation on aluminum, they found that positively charged particles, now known as positrons, a positively charged counterpart to negatively charged electrons, continued to be emitted even after the alpha radiation was stopped. The number of positrons emitted decreased by half every 3 minutes. This was an important clue to what was going on. By then, it had been well established, chiefly by Ernest Rutherford, that any naturally occurring radioactive element decays in this way. However much or however little of the element you start with, half the nuclei transform into nuclei of another element and spit out radiation such as positrons in a certain time. Half of the remainder decay in the next interval, the same length, and so on. Each radioactive element has a characteristic half-life, some measured in fractions of a second, some measured in millions of years. So the Joliot-Curies knew that they were observing true radioactivity from an element with a radioactive half-life of about 3 minutes. Their experiment involved both the transmutation of one element into another and the artificial creation of radioactivity, as Irene later explained. Returning to our hypothesis concerning the transformation of the aluminum nucleus into a silicon nucleus, We have supposed that the phenomenon takes place in two stages. First, there is the capture of the alpha particle and the instantaneous explosion of the neutron, with the formation of a radioactive atom which is an isotope of phosphorus of atomic weight 30, while the stable phosphorus atom has an atomic weight of 31. Next, this unstable atom, this new radio element which we have called radiophosphorus, decomposes exponentially with a half-life of 3 minutes. Before this discovery, radioactivity was a property associated only with about 30 naturally occurring elements. The artificial creation of radioactive elements opened up a whole new field of research. The Joliot-Curies quickly extended their work to experiments involving other elements and found that they could produce radioactive elements from boron and magnesium. Bombarding boron with alpha particles produces an unstable form of nitrogen with a half-life of 11 minutes, while bombarding magnesium and with alpha particles produces unstable isotopes of silicon and aluminum. For all this work, Irene and Frederick shared the Nobel Prize in Chemistry in 1935, the same year that Chadwick received the Nobel Prize in Physics. Their citation read, "In recognition of their synthesis of new radioactive elements," his was for the discovery of the neutron. Looking ahead in his Nobel lecture, Frederick Joliot-Curie accurately assessed some of the long-term implications of this work. If we cast a glance at the progress achieved by science at an ever-increasing pace, we are entitled to think that scientists building up or shattering elements at will be able to bring about transmutations of an explosive type, true chemical chain reactions. If such transmutations do succeed in spreading in matter, the enormous liberation of usable energy can be imagined. But unfortunately, if the contagion spreads to all the elements of our planet, the consequences of unloosing such a cataclysm can only be viewed with apprehension. Within 10 years of those words being uttered, the first nuclear bomb was exploded. Moving on to the vocabulary section. Emitter, emitting. Knock. Notice we don't pronounce K. Knock. Paraffin or paraffin. Neutrons, positrons. Decays, half-life. Fractions of a second. Fractions of a second. Transmutation. Transmutation. Instantaneous explosion. Instantaneous explosion. Decomposes exponentially. Decomposes exponentially. Glance. Cast a glance. Building up. Shattering down. Enormous. Enormity. Enormous. Fortunately. Unfortunately. Cataclysm. Cataclysm. Apprehension. Apprehension. Thank you so much for your time, and I will see you in the next story, and it's a very special story. Bye for now.